Welcome back, everyone. Today we're going to be talking about correlations. If you recall from previous videos, we've used contingency analyses to assess associations between two categorical variables, or t-tests or ANOVAs to assess the effects of some categorical explanatory variable on some continuous numerical response variable. But what we want to talk about next is how we can assess the relationship between two continuous numeric variables using the techniques of correlation and regression. Now, this video is going to be about correlation, and in the next video, we'll talk about the procedures of regression. So in a correlation, we're interested in assessing how two variables are associated with one another. So for example, is there an association between body mass and brain mass across these different mammal species? So in this plot, we've plotted the brain mass against body mass for each of these different mammal species. And it looks like overall there's a positive association where the larger the body mass, the larger the brain mass. Now, in this case of a correlation, we're not really interested in trying to fit a line or to make predictions about brain mass from body mass. We're just trying to assess whether there's an overall association between these two variables. And that's what's referred to as a correlation. The linear correlation coefficient then measures the strength of association between two numeric variables. And we use little r to refer to the correlation coefficient from our sample. Now, just like for means and variances and standard deviations, we differentiate between the population correlation and the sample correlation by using the Greek letter rho to represent our population parameter, and we use the Latin letter r to refer to the estimate of this population parameter that we take from our sample. So here we have 4 different plots representing 4 different correlation coefficients. A correlation coefficient can range between -1 and 1. Strong positive associations are represented by values closer to 1. Strong negative associations are represented by values closer to -1, and no association between our two variables is represented by a correlation coefficient equal to 0. Now, it's important to note that correlation coefficients are linear relationships. Now, in the plot on the left, there's a positive correlation of 1. In the plot on the right, even though the two variables are tightly related to one another, the relationship is fundamentally nonlinear. And as a result, the linear correlation coefficient is actually equal to 0. There is no net positive or negative relationship between these two variables. So how can we quantify our correlation coefficient then? Well, the correlation coefficient is equal to the covariance between our two measurements divided by the geometric mean of the variance in X and the variance in Y. And what I mean by the geometric mean is simply the two variances multiplied together, and we simply then take the square root of the product of those two variances. So what is this term covariance then? Well, a covariance is simply a measurement of the degree to which two variables vary together. When one variable is higher than average, is the other variable consistently also higher than average, representing a positive covariance? Or when one variable is higher than average, is the other variable consistently lower than average, representing a negative covariance? Alternatively, we might have no covariance at all if when one variable is higher than average, the other variable isn't consistently higher or lower than average. Now, to walk through an example of a covariance, I'm going to use some data that were presented in a recent Washington Post article about the relationship between wearing a mask and the prevalence of COVID symptoms across each of 50 different states within the United States of America. Now, these data come from a Facebook poll where respondents were asked whether or not they wear a mask in public most or all of the time. And they were also asked whether or not they knew anyone with COVID symptoms. And so here we have along the x-axis the percentage of respondents who wear a mask in public most or all of the time, plotted against the percent of respondents who knew someone with COVID symptoms. And each data point represents the value for one particular state. Now, in this plot, we can see that there's a negative relationship between the percent of respondents who say they wear a mask and the percent of respondents who know someone with COVID symptoms. This suggests that there's an overall negative covariance between these two variables. States with lower than average mask wearing have higher than average COVID symptoms. In contrast, states with higher than average mask wearing have lower than average COVID symptoms. So let's walk through some of the data from this survey to see how we can go about calculating a covariance. Now, these aren't all of the data, but I've just reported the first few states from the data set. And what you can see is that for each state, we have the percent of respondents who reported wearing a mask most or all of the time in public, and the percent of respondents who know someone with COVID symptoms. So for Alaska, 82% of respondents reported wearing a mask most or all of the time in public, and 33% of those respondents in Alaska reported knowing someone with COVID symptoms. Now we can calculate the average percentage of respondents across the entire data set of 50 states to find that on average, about 83.4% of respondents wear a mask in public. In contrast, 24% of respondents know someone who has COVID symptoms. So we can calculate a covariance then, first of all, by calculating how different each observation of mask wearing is from the mean amount of mask wearing, and how different each observation of reported COVID symptoms is away from the mean for COVID symptoms. And that's what I mean by X sub I, the X value for state I, minus the mean for all of the states that we considered. We can do this and find that respondents in Alaska reported wearing a mask a little bit less than average, and they reported knowing someone with COVID symptoms greater than average. And so what I can do just for the purpose of demonstration is to make the observations that were greater than the mean reported in blue font instead of black font. And what you can see is that when mask wearing was less than average, it looks as though COVID symptoms were greater than average. And when mask wearing was greater than average, most of the time, COVID symptoms were less than average. And so we can see right away that negative values of one variable tend to be associated with positive values of the other, meaning when mask wearing is less than the mean, COVID symptoms are greater than the mean. And when mask wearing is greater than the mean, COVID symptoms are less than the mean. Now, this is just examining these patterns in a really qualitative way. But the way we calculate a covariance is by taking these two deviations from the mean and multiplying them with one another. And so when we have a value less than the mean multiplied by a value greater than the mean, we get a negative product. And when both values are negative, we get a positive product. But the product then also depends on the magnitude of these deviations. When we have really big deviations above and below the mean, we get a really big product. And so we can calculate our covariance between these two variables essentially as the average of these products across all of the 50 states that we examined. So to calculate our covariance then between these two variables, we sum up the product of the first variable's deviation from its mean multiplied by the second variable's deviation from its mean. And we add those all up across all of our observations and divide by the number of pairs minus 1. So in this data set, we had observations from 50 states. So we would sum up those products across all of the 50 states and divide by n minus 1, or 49. And when we calculate the covariance then for the relationship between mask wearing and COVID symptoms, we calculate a covariance of negative 53.37. Now, this equation for the covariance might look a little bit familiar to you because it actually looks quite similar to our equation for a variance. So let's, for example, just take this wacky scenario where we calculate what the covariance is between a variable and itself. So what's the covariance between x and x? Well, it's the sum of all deviations of x from the mean of x multiplied by the same value over again. And if we simplify this equation a little bit, we're talking about the sum of squared deviations of each observation from the sample mean. And so we can tell from this that a covariance between a variable and itself is just the variance. So we can take our covariance that we've just calculated, divide it by the square root of the product of the two variances to calculate our correlation coefficient of the relationship between mask wearing and COVID symptoms across these 50 states as negative 0.85. Now remember that a correlation coefficient is a number between negative 1 and 1. So we can see that this negative 0.85 correlation is a very strong negative correlation between the percent of mask wearing and the percent of people who know someone with COVID symptoms. But is this correlation coefficient actually different from 0? So in this case, our null hypothesis is that the true correlation coefficient, rho, is equal to 0. That is, that there is no correlation between x and y. Now, when this null hypothesis is true and the true correlation is 0, then our sample estimates of R will be normally distributed with a mean of 0, and we'll have degrees of freedom equal to n minus 2. We can then calculate a test statistic for our correlation coefficient equal to the correlation coefficient divided by the standard error of the correlation coefficient, which is equal to the square root of 1 minus r squared divided by n minus 2. We can use R to test whether our correlation is different from 0 using the core test function, where we simply specify the two variables within the parentheses. So in this example, my data frame is called COVID, one variable is called percent mask, and the other variable is called percent symptoms. And we can see that we get our estimate of the correlation coefficient, as well as 95% confidence intervals for this correlation coefficient. We also calculate a t-test statistic, degrees of freedom equal to 50 states minus 2, and our p-value associated with a t-test statistic of negative 11.3 and 48 degrees of freedom is very, very small. So in this case, we would conclude that the correlation between the percent of respondents who wear a mask and the percent of respondents who know someone with COVID symptoms is significantly negative. Just like our other statistical tests, there are certain assumptions associated with a test of correlations. First of all, we assume that our observations are random and independent. Second, we assume that our X variable, or one of our variables, is normally distributed with equal variance across all values of Y. And second, that the converse is also true, that Y is normally distributed with equal variance for all values of X. Now, it's also important to point out that a correlation can change depending on what range in the data we're looking at. Now, if you recall from our statistical assumptions that X and Y are interchangeable with one another in a correlation. That is, there is no clear predictor and no clear response when we're talking about a correlation. So it doesn't really matter which variable we put on the x-axis and which variable we put on the y-axis. So correlations then measure the association between two continuous variables. In a correlation, there is no clear predictor and clear response. These two variables are interchangeable with one another. A positive correlation means that larger than average values of X are associated with larger than average values of Y, whereas a negative correlation means that larger values of X are associated with smaller than average values of Y. Correlations are defined to range between -1 and 1, where a value of 0 represents no correlation at all. When the null hypothesis is true, that is, that the true population correlation is equal to 0, then R will be normally distributed with a mean of 0. And we can then use a t-test statistic to test whether our observed correlation is different from 0.